So today's video is on catalysts. So first we're going to have a look at what catalysts are. So a catalyst is a substance that speeds up a chemical reaction by lowering the activation energy. And the activation energy is the minimum amount of energy needed for a reaction to start. So if you see here on our reaction diagram, our normal reaction needs a much larger activation energy, has a much larger activation barrier to overcome. And with the catalyst, the activation energy is much lower, meaning the reaction will be quicker because the molecules will overcome this activation barrier much quicker. And a catalyst can be recovered unchanged from a reaction, so it is not chemically changed during a reaction, so it can be reused. And catalysis is the process of speeding up a chemical reaction with a catalyst. So now we're going to have a look at a few more key terms. So homogeneous catalysis is when the catalyst and the reactants are in the same state. So for example, if both the reactants and the catalyst are in the gaseous state. And then we have heterogeneous catalysis, and this is when the catalyst and reactants are in different states. So if we have a solid catalyst with gaseous reactants. And then we have cracking, which is splitting large molecules down into smaller ones. So we're going to have a more of a look at cracking now. And so cracking in these terms would be long chain alkenes are being broken down into shorter, more useful hydrocarbons. And these useful hydrocarbons can be shorter alkanes, which are usually highly branched, or they can be alkenes, which contain a double carbon bond. And catalytic cracking is when we have we're heating our heavy oils in the presence of a catalyst, meaning we speed up the cracking process. So some common products of cracking. So if we crack alkanes, we can produce branched alkanes and branched alkenes. And if another product of cracking alkanes is smaller alkanes and cycloalkanes. And so we know that cycloalkanes and alkenes are functional group isomers, meaning they're made of the same molecules but with different structural arrangements. So we know that this can work. And then if we crack cycloalkanes, we can produce branched alkenes and alkenes. And lastly, if we crack alkenes, we will create smaller alkenes. And so now we're going to have a look at the process of cracking, process of catalytic cracking. So first we have to start with a rise reactor, and this is a modern catalytic converter. And so the first step in this is when our vaporized hydrocarbons, so in the gaseous state, and our zeolite catalyst, which is a solid catalyst, they are fed into the bottom of the rise reactor and are forced upwards by steam. So we now can tell that we have our reactants in its gaseous form and we have our catalyst in its solid form. So this is going to be heterogeneous catalysis. The reactants and catalysts are in different states. So with this, we can imagine the vaporized hydrocarbons entering this rise reactor with the solid catalyst, and steam forces them to rise up. And it takes only 2 seconds for this mixture of hydrocarbons to flow from the bottom to the top of the rise reactor. So this means that the hydrocarbons are actually in contact with the catalyst for a very short amount of time. And during this process of rising up the rise reactor, coke, which is carbon from the decomposition of our hydrocarbons, forms on the catalyst. So it forms around this zeolite catalyst, and this eventually makes our zeolite catalyst inactive. And then after this step, the separator is used, and this is when steam carries away the cracked products from our hydrocarbons, and this leaves our solid catalyst, our solid zeolite catalyst, behind, and it's covered still in this coke. It's carbon from the decomposition of our hydrocarbons. And so our zeolite goes to the regenerator, and in the regenerator the coke is burnt off, and so this reactivates the catalyst. And then the zeolite, once it's been reactivated, is reintroduced to the bottom of the RISE reactor again to start this process over again. And this regeneration of our zeolite catalyst is actually very advantageous, because heating our catalyst and burning off all the coke, while it reactivates the catalyst, it also allows the feedstock to be cracked without additional heating. So the heat that we've applied to our catalyst is enough to crack our products. So we don't have to introduce any more heat, use any more energy. But the main question is, how does a catalyst actually work? And so we're going to be looking at that now. So these are the steps of how a catalyst works, and we're going to be working through them. So our reactants, either liquid or gaseous, form bonds with the atoms on the surface of the solid catalyst. So we can see straight away that this is another example of heterogeneous catalysis, because our reactants and catalyst are in opposite states. And after they have formed bonds with the surface, they are adsorbed to the catalyst. And so the difference between absorption and adsorption is that in adsorption, the reactants will form bonds at the surface, while with absorption, they'll be taken into the substance. So they are adsorbed, they're held on the surface of the solid catalyst like a film, as we can see here. And this adsorption causes the bonds in our reactant molecules to weaken. And once we've weakened the bonds in our reactants, this allows new bonds between the reactants held close on the surface to form, to make our products. So, for example, if we have this, if these two molecules adsorbed to the catalyst are our two reactant molecules, then because their bonds are weakened, they will be more likely to form the product between them. And once the bonds between our products are formed, this weakens their bonds with the catalyst, so our product is eventually released. So a catalyst basically weakens the bonds of our reactants when they are adsorbed, and this means it's more likely to form bonds with the other reactants to form our products. And lastly, we're going to be looking at catalyst poisoning. And catalyst poisoning is when a substance blocks the active sites of our catalysts, making it inactive. So this means that our reactants cannot be adsorbed to our catalyst, meaning it cannot work. And some catalyst poisoning is temporary and some is permanent. So we saw earlier on in the video that zeolite, it can be covered in coke, which inactivates it, but our coke can be burnt off. So this is temporary catalyst poisoning. So leaded petrol, however, cannot be used in cars with catalytic converters. And this is because our lead is a catalyst poison that will cover the catalysts in the catalytic converters, and this is a permanent poisoning. So once the catalyst is covered in this lead, it cannot be removed and the catalyst cannot be reactivated. And processes which use catalysts will need to remove substances that would cause catalytic poisoning. So, for example, in the Haber process, a nickel catalyst is used, and this nickel catalyst would be poisoned by sulfur compounds. So sulfur would block the active sites, making the catalyst inactive and unable to increase the rate of reaction in our Haber process. So this means that before the process begins, they will need to remove any sulfur compounds from the feedstock to ensure that no catalytic poisoning occurs.